Okay, in example 7, we're going to combine a shift and a stretch. So we're going to sketch a graph of f of x, which is equal to 5 times the log of x plus 2, state the domain, the range, and the asymptote. So remember, what happens inside the parentheses happens first. So first we move the graph left 2 units, then stretch the function vertically by a factor of 5. The vertical asymptote will be shifted to where c is equal to -2, so x is going to equal -2 is the vertical asymptote. The x-intercept will be -1, 0. Now the domain will be -2 to infinity, since we shifted it to the left 2 units. The 2 points will help give the shape of the graph is -1, 0, and 8, 5. We chose x equals 8 as the x-coordinate of one point to the graph because when x is equal to 8, x plus 2 is equal to 10, which is the base of a common logarithm. So in this scenario here, since we're only dealing with increments of 1, and it goes to 5 on each side of the x and y axis, and the same thing on the y axis. So I'm going to show you how I plot. If we plotted 1, 2, and 3 into the general parent function, if x is 1, then the log of 1 is 0. If x is 2, the log of 2 is 0.3, and I'm just rounding it to one decimal place. If x is 3, then the log of 3 is 0.5. So I'm just going to follow my rules. So if this is the original point, 1, 0, on that graph, so if we take a look at that original point, which is 1, 0, then what we're going to do is we're going to add c to the x-coordinate and then multiply a by the y-coordinate. So we're going to have y minus 2, 5 times 0, which leaves us with -1, 0. And if you notice here, we're going to plot that point. There is -1, 0 on the new graph. If we take a look at our 2, 0.3, again, it's 2 plus c, and a times the value of 0.3. So 2 minus 2 is 0. 5 times 0.3 is 1.5. So we're going to have 0 and then 1.5 as another ordered pair on that graph. Same thing with 3 and 0.5. If we have 3, we're going to add c to that, meaning we're going to subtract 2, which gives us 1. And then the factor of 5 times 0.5 is 2.5. So if you take a look at 1, and then up here is 2.5. So those are the 3 points on the graph. Now what they've done over here is that you can use the values that are going to make it easier to find the logarithm of a power of 10. Since the base is 10, if we find the logarithm of 10, so what exponent do you have to multiply to get 10? So if the base is 10, that means 10 to the first power. Now, that would be 1. If we put in 100, so what is the exponent on base 10 to get 100? Well, that would be 10 squared, so that would be 2. If we put in 1,000, again, the reason why we're using powers of 10 because this is a common logarithm that has a base of 10. So then what is the power, or what is the exponent on base 10 to get 1,000? Well, that would be 3. So that's another way of plotting those points, but since our graph doesn't go all the way up to 10 or 100 or 1,000, then we're going to have to use these points for 1, 2, 3, 4, and 5 like we did at the beginning.